Assalamu alaikum and greetings everyone to our group Ali and Muqbil, and today we will present our HPPC final project. Our project is called Performance Evaluation of OpenMP based Parallel Image Pre-Processing for AI applications with Energy Efficiency Analysis. This project is under Theme 1, AI Accelerated Parallel Computing. In this presentation, we will explain the problem, our solution, the implementation, the result, and finally, what we learned from this project. So now, let's go with the problem overview. Nowadays, many AI systems process thousands of images every day. Before AI can recognize objects, every image needs some processing first. Some common steps are converting the image to grayscale, removing noise with using blur and finding edges with using the spool filter. If all images are processed one by one, takes a lot of time because only one CPU core is working. The other CPU cores stay idle. Our idea was simple. Can we use OpenMP to process many images at the same time? And if we can, how much faster will it be? We also wanted to know which number of threads gives the best performance while using less energy. So our objectives has four main is four objectives, which is the first one. We built an image pre-processing pipeline in C++. The second, the pipeline includes uh, no, in C++, the pipeline includes grayscale conversion and blur and Sopel edge detection. The second, we create both a serial version and a parallel version using OpenMP. Going with the third objective, which is we compared their performance by measuring execution time, speed up, and efficiency and scalability. Finally, completed the bounce task by studying energy efficiency and finding the best read configuration. Now I pass to Mokbil to explain the system design.
Okay, thank you, Ali. So this slide shows how our program works. The program starts from the main.cpp. Then the dataset manager reads all images from the selected folder. Next, the benchmark engine runs both the serial and parallel versions. So each image goes through the same step. First, the image is loaded, then it's converted to grayscale. After that, Gaussian blur removes noise. Finally, Sobel edge detection finds the edge. So the processed image is saved and the execution time is recorded for later analysis. So we separated the program into different modules to make the code easier to understand and maintain. So this slide shows the image processing pipeline. On the left, we have the original image. The first step is grayscale conversion. This removes the color information and keep only the brightness of the image. The second step is the Gaussian blur. This makes the image smoother and removes the small noise that may affect the next stage. And the final step is Sobel edge detection. This detects the edges and important shapes in the image. So these three steps are very common in computer vision and AI application because they prepare the image before it's sent to an AI model. So to design our parallel solution, we used Foster's BACM method. So the first step in this method is partitioning. Partitioning. We divided the work by image. This means every image is treated as one independent task. So the second step is the communication. Since every thread work on different image, they do not need to communicate with each other. So this makes the program simple and efficient. The third step is agglomeration. Instead of creating many very small tasks, we keep one complete image as one task. So this reduces extra work for the processor. And the last step is mapping. So OpenMP automatically shares the images between the available threads using parallel for, because every thread works on its own image. There is no race conditions, and the program runs safely. So for the implementation, this slide shows the difference between the serial and parallel versions. In the serial version, images are processed one by one using a normal for loop. In the parallel version, we used OpenMP with hash pragma OMP parallel for. We also use dynamic scheduling. This helps OpenMP distribute the work more fairly between threads. So another important part is reduction. It's also that it allows all threads to safely count the number of processed images without causing any errors. So the good thing is that both versions use almost the same code. The main difference is adding the OpenMP directives. Now I will pass the presentation back to Ali, who will explain the testing method and the performance results.
Okay, so now I will explain how we tested our program. We used a data set that contains 600 images. Each image has a resolution of 480 by 480 pixels. To make our results more reliable, we didn't run the program only once. Instead, we repeated the test several times and used the maiden result. We tested the program using one thread, two threads, four threads, and eight threads. Then we measured the execution time using the C++ chrono library. After collecting the results, we calculated the speed up, efficiency, throughput, and energy efficiency. So now this slide shows our performance result. The graph on the left shows the execution time. As we can see, using two threads reduced the execution time a lot compared to using only one thread. The graph on the right shows the speed up. So the best speed up we achieved was about 1.74 times. After two threads, the performance did not improve much. This happened because our testing machine only had two logical processor. When we used more than two threads, the extra threads had to share the same hardware resources. So instead of making the program faster, they added some extra overhead. This is exactly what we expected based on Amdahl's law. So as you can see, this slide shows the efficiency and scalability of our program. The highest efficiency was 87%, and it happened when using two threads. When we increased the number of threads to four or eight, the efficiency became lower. This is because the CPU was already fully used with two threads. The throughput graph also tells the same story. So the number of processed images per second increased a lot when moving from one thread to two threads. After that, it stayed almost the same. So these graphs tell us that adding more threads does not always mean better performance. The best choice depends on the available hardware. For the bounce part of the project, we studied energy efficiency. Instead of looking only execution time, we also looked at how efficiently the CPU resources were used. Our result shows that two threads gave the best balance. It finished the work faster while using less relative energy. Using four or eight threads did not improve performance, but it used more CPU resources. So based on both performance and energy, two threads was the best configuration for our system. Now I will pass the presentation back to Mokul for the final part.
Okay, thank you, Ali. So this slide summarizes the most important result of our project. So the best configuration was two threads. With this configuration, we achieved 1.74 times speed up, and we also reached 87% efficiency while reducing the relative energy to about 58% of the serial version. So, in addition, the program processed around 466 images every second. So this result shows that choosing the correct number of threads is more important than simply choosing the largest number. So for the lesson learned during this project, we learned several important lessons. First, parallel programming can greatly improve performance when the problem is suitable for parallel processing. Second, using more threads than the available hardware does not always make the program faster. Third, good benchmarking is very important. Uh, and lastly, without proper measurement, it is difficult to know whether the program is really improving. And finally, we learned how OpenMP makes parallel programming much easier compared to creating threads manually. So to conclude this, we successfully developed an image pre-processing application using C++ and OpenMP. We compared the serial and parallel versions and measured their performance. And our result shows that OpenMP reduced execution time while also improving the energy efficiency. And overall, this project helped us to understand how parallel computing can solve real-world problems in AI image processing. So for future work, we would like to test the program on computers with more CPU cores. And we wanted to use MPI with OpenMP and also study GPU acceleration using CUDA. So I think that's all. Thank you for very much for listening.